Alright, welcome to page 3. This is example 2, a mass weighing 32 pounds. Page 3, this is example 2, a mass weighing 32 pounds stretches a spring 2 feet. Determine the amplitude and period of motion if the mass is initially released from a point 1 foot above the equilibrium position with an upward velocity of 2 feet per second. How many complete cycles will the mass have completed at the end of 4 pi seconds? And so we notice that we are given pounds again, so we're going to do, to find our mass, it's going to be W equals M times G, where G again is that pull of gravity. So our weight is 32 pounds. That's equal to M times 32. Again, we're using 32 because we're talking about feet. And so that means that our mass is going to be 1. To find our K, again, it's we use Hooke's law, which is the force is equal to K times S. And so we're stretching the spring by 2 feet. So that's why that's 2. So therefore our K is going to be 16. Now, our initial position is equal to -1 because where we're going to start, it says that it's initially released from 1 foot above the equilibrium position. Because we're above, that's why it's negative. Alright? If it was below, it's positive. And so because we're working kind of against the pull of gravity, that's why it's -1. Right? And we're not working with the pull of gravity. Our x prime is 0. Our initial velocity is going to be -2 because it gives us with an upward velocity of 2. So because velocity is going up, that's why it's negative. So it's upward velocity. And so what we want to do is we want to find, okay, well, what is our omega? And so our omega squared is just K over M. Well, we know what our K is. Our K is 16. Our M is going to be 1. And so therefore our omega squared is 16, meaning our omega is going to be 4. Now, because of the conditions that were given in the example, I know, again, this is a second order differential equation where, again, we do not have any retarding forces upon our spring, so therefore it's going to have this form, and we know that the solution always for these forms are going to be the position function is equal to c sub 1 cosine wt plus c sub 2 sine of wt. I'm sorry, not w, but omega t's. Alright, so x of t is equal to c sub 1 cosine of 4t because 4 is omega, so plus c sub 2 sine of omega t, which is 4t. Alright, now to find our c sub 1 and our c sub 2, what we're going to do is we're going to plug in using our initial position and our initial velocity. So when I plug in for the initial position, it's going to equal to -1. And -1 is equal to, we substitute in all of our t's for 0, and so we are just only left with c sub 1, so -1 is equal to c sub 1. To find c sub 2, we have to take the derivative of our position, and when we take the derivative, we're given -4 c sub 1 sine of 4t plus 4 c sub 2 cosine 4t. Substituting in our initial velocity, -2 is equal to 0 is our t, so the sine part's going to cancel out. We're left with 4c sub 2 on the right-hand side equal to -2. So that means c sub 2 is equal to -1/2. So our position function is just x of t is equal to negative cosine 4t minus 1/2 sine of 4t. Now, there's a few questions that it's asking. It then asks how many complete cycles does the mass have, will the mass have completed at the end of 4 pi seconds? And also it wants us to determine the amplitude and period of motion if the mass is initially released. So the period of motion and the amplitude as well. So the period of motion is not going to be too difficult. Here's the period of motion again. Going back to the previous page too, it gives us that the period of motion is just 2 pi over omega, and our omega was 4, so 2 pi over 4, so pi over 2 seconds is how long it takes to complete one cycle. And how many cycles we'll have complete at the end of 4 pi seconds, well, then that should be pretty easy as well, because all we would have to do, if it takes, pi over 2 seconds to complete one cycle, then we should know that, after 4 pi seconds, it's going to be able to go through 8 cycles. But we also have the formula for per second. So here we have omega over 2 pi. That's going to be 4 over 2 pi times 4 pi, which is the number of seconds that we're going to go by, and that gives us 8 cycles. Now, the hard part is finding the amplitude, because when we look at a trig function, we're usually just looking at either sine or cosine, and the coefficient that's in front of cosine is our amplitude. So what we want to do is we want to change our position function that we have right here in terms of either sine or cosine. So I'm going to change this one in terms of cosine. I'm going to show how you can either change it in terms of cosine or sine. Here I'm going to show you how you can change in terms of cosine. So what we're going to do is we're just going to change it to be our amplitude of cosine, our amplitude times cosine of WT minus phi. All these Greek letters. So to find our amplitude, all it is just the square root of our constant squared, so c sub 1 squared plus c sub 2 squared. Or c sub 1 was -1. Our c sub 2 is -1/2. When we square both of those, we get 1 1/4. Add those, we get the square root of 5 over 2. To find our omega, it's just taking pretty much the tangent of this, and so the tangent of omega is going to be c sub 2 over c sub 1. And again, c sub 2 is -1/2, c sub 1 is -1. We get 1/2. So omega is equal to, so tangent of omega is equal to 1/2. Take the inverse tangent of both sides. We get 0.45. Now, there's a problem with this, and that is both our c sub 2 and our c sub 1 were negative. So that tells us that we were not in the first quadrant. We were in the third quadrant, and we got a value that gave us a value in the first quadrant. So in order to find the value in the second quadrant, all we would have to do is just add pi to our solution. So our phi, I think I said misspoken a few times with my Greek letters, but our phi is 3.605. And so now that we found our phi and our amplitude, we can go ahead and write it in this form, where x of t is equal to the square root of 5 over 2 cosine of 4t minus our phi, which is 3.605. So that means that our amplitude is the square root of 5 over 2. Now, again, you didn't have to do all of this. I just wanted to show you how you could change it all to cosine, because all we needed was that amplitude. Now, leads us to the next one, alternate forms of x of t. I just showed you how you could do an alternate form using cosine. Here's an alternate form using sine. So say our position function is c sub 1 cosine of omega t plus c sub 2 sine of omega t. We can change this in terms of sine or cosine. Now, if we're changing this in terms of sine, instead of minus our phi, it's going to be plus phi. Amplitude is the same thing. It's the two constants squared, and our phi is going to be defined in this case by sine and cosine. And for our tangent of phi, it's going to be c sub 1 over c sub 2. If you remember from just the previous example, when we're using cosine, it's c sub 2 over c sub 1. When we're looking to find sine, it's c sub 1 over c sub 2. Now, we want to verify why this is. Well, what we can do is we can do an angle sum formula. So we can break up our sine. If we break up our sine into the angle sum, it would just be a sine of WT times cosine phi plus a cosine WT times sine of phi. So we broke this up into angle addition. And when we do that, we can rewrite a few things. I can change a cosine omega t sine phi to just a sine phi cosine omega t plus a cosine phi sine omega t. The reason why I kind of rewrote it this way is just so that we could bring this back to the position function. We know that a sine of phi, sine of phi, given this, is c sub 1 over a. So I'm going to change sine of phi to c sub 1 over a. The a's will cancel out, and I'm just left with c sub 1 cosine of omega t, which looks exactly like that. And when I substitute in for cosine phi, that's c sub 2 over a. And so therefore the a's cancel out, and I get c sub 2 sine of omega t. So it's the same thing, we're just writing it a different way. It's an alternate form. But it helps us find the amplitude.